Okay, let us continue with the subtopic of stereochemistry, which is conformation and reactivity. Now, earlier we have done what is called the static stereochemistry. We have done the conformation analysis of various conformations and how the energy varies with that, and which type of molecule will prefer one conformation over the other, and the reason for such type of preference, that we have discussed. Now, in the dynamic stereochemistry, the first thing that was very relevant was the Cartin-Hammett principle, because in dynamic stereochemistry now you have conformational flexibility. So, one conformer goes to the other conformer, and it may so happen that one conformer leads to one compound and the other conformer leads to another compound. So, the question is what will be the ratio of the two products. These products ratio, according to Cartin-Hammett principle, if the conformational flexibility barrier is low, that means it is happening at a very rapid rate as compared to the rate of the reaction, then what happens? The ratio of the two products is not dependent on the population of the conformers in the ground state. It depends on the difference in the free energies of the respective transition states for the two processes. Okay. And we have given some examples. However, as I said, the Cartin-Hammett principle, usually what happens, that the more stable conformer gives the major product. That means, the conformer which is more populated is giving the major product. So, that people might say that the formation of the major product was due to the greater population of the starting conformer. Now, to really prove it, the best way is to, if I can show that the less stable conformer, that means the less populated conformer giving the major product. And yesterday I have given you an example of a bicyclic compound, where alkylation is happening from a less populated conformer. So, that really proves experimental proof for the Cartin-Hammett principle. Now, we will elaborate on this Cartin-Hammett principle, but last time you remember that I told you about the preference of certain conformers to have axially oriented groups, like in case of 1,3 cyclohexane diol, where hydrogen bonded plays a key role in forming the diaxial conformation. Then dihalo system, 1 to dihalo system, in order to reduce the repulsion between the two halogens, negatively charged halogens. The molecule also takes a conformer where the halogen groups are axial. Okay. And we have also seen that there is an effect called the alkyl ketone effect. We have seen the 2-alkyl ketone effect, the 3-alkyl ketone effect, and I told you briefly about the 4-alkyl ketone effect. I will just tell something about the 4-alkyl ketone effect. The alkyl ketone effect arises because of the presence of the ketone in the cyclohexane system. The presence of the ketone, what it does, it immediately affects the hydrogens in the equatorial positions. This bond is now almost eclipsed to this carbonyl. In addition to that, you have now, if you have a group here, there is only one hydrogen at the axial position in 1,3 relationship, where the 1,3 diaxial interaction takes place. So, by putting this carbonyl, first of all you are incorporating this eclipsing interactions, and you are reducing 1,3 diaxial interaction. So, what happens here, that there is a substantial amount of the, if it group is R, then there is a substantial amount of this going into the axial orientation, and this effect is called 2-alkyl ketone effect, because it is in the 2 position with respect to the carbonyl. If there is a R here, then also because of the reduction of 1,3 diaxial hydrogen, this conformer will also be present in substantial amount, in greater amount as compared to a cyclohexane system. So, this is what is called the 3-alkyl ketone effect, and there is also this was done by Eliel. He showed that there is also 4-alkyl ketone effect that is also present, although this is quite remote from this, but it is due to the fact that because of the flatness of these two the carbonyl and the two carbons, the flatness of this ring. So, these hydrogens are little bit bent towards this direction. So, if that happens, then what happens if you have a methyl here and a methyl here. So, this methyl suffers less 1,3 diaxial interaction as compared to a cyclohexane system. Okay. So, how do you know that it suffers from less interaction? The experiment to do is that you take dimethyl cyclohexanol, and you take cyclohexanol. So, this is 4,4-dimethyl cyclohexanol and this is cyclohexanol. Now, if you oxidize it, you will see the rate of oxidation, suppose this is R1 and the rate of oxidation this is R2, you will see that R1 is greater than R2. This is because that in this oxidation you are releasing the 1,3 diaxial interaction suffered by this axial methyl. If it is in the alcohol form, then there is these are in the normal 1,3 diaxial mode, but as soon as oxidation takes place. So, there is a release of this steric strain, that 1,3 diaxial interaction. So, this undergoes oxidation faster, the oxidized product is this, but this undergoes oxidation slower. Okay. So, this is what that means. This is giving some stability to the system, okay, and the stability arises due to these two hydrogens being bent away from the methyl group. Okay. So, thus reducing the 1,3 diaxial interaction. This is what is called the 4-alkyl ketone effect, because now you have 1, 2, 3, 4. So, this is 4-alkyl ketone effect. So, I thought just to complete the whole thing, because I said about 2-alkyl ketone effect, 3-alkyl ketone effect quite elaborately. So, I should say about something about 4-alkyl ketone effect and why does it originate, that is the important thing, because of the bending of this CH axial hydrogens. Okay. Similarly, yesterday also I again told another kind of system where there is significant amount of axial substituent, and that happens in very similar system like the cyclohexanone, only thing that you have a double bond here, exocyclic double bond with substituents R1, R2 and R1. So, here what happens now, if there is a group here, so that is now undergoing steric compression with this R1. So, as a result this undergoes flipping and you get this R as axial. So, now there is no steric compression between the R1 and R. So, R1 that one is there. Okay. So, that is now gone, that is not present. So, there is significant amount of this axial conformer, and this is what is called A13 strain. A13 strain. Okay. Now, because this is 1, this is 2, this is 3. So, that is the origin, the name how it originates. Now, instead of there is another one that is called A12 strain. If the double bond happens to be in the inside of the ring. So, if the double bond happens to be a that means you are talking about a cyclohexene. Okay. And in cyclohexene there will be an interaction between these two groups, and this interaction of R2 with R1 will depend upon whether R2 is axial or in the equatorial conformation. However, orientation. Now, the question is, we have not done the how the this cyclohexene looks like. We have done the cyclohexane, but just to let you know that cyclohexene exists as a conformer which looks like this. sorry. It is somewhat like this. So, it's what happens here that one carbon, these, see basically this is a double bond. So, this carbon, that carbon and this carbon, these are in the plane. How many? 1, 2, 3, 4, sorry, 5, 6, 7. So, this is the cyclohexene. So, these 4 carbons are in the plane, and then one carbon it goes above the plane, another carbon goes below the plane. Okay. Now, if you have a substituent here and a substituent there, this is called the equatorial, pseudo equatorial you can call. This is not perfectly equatorial like the cyclohexane, and this is the axial position. Okay. So, if it first of all, this is not a planar system, this is a kind of what is called a half chair type of conformation, and in the conformation you must clarify that 4 carbon atoms are in the plane, 1, 2, 3, 4, and this goes down and this goes up, this goes down and this goes up. So, this is in the plane of this because of the double bond sp2 nature. Okay, that has to be. Now, this R2 is in the equatorial orientation. If it is in the equatorial orientation, it suffers from now steric compression with R1, because there is a lot of kind of they are very close to each other. So, that flips and it takes a conformation where, let us see how to draw it. So, it takes a conformation where so a conformation 1, 2, 3, 4, 5, 6, 7, no, see this is 7. So, something like this, that is the flipped form, and the R1 goes to the top, R2 goes to the top, sorry, and this is the R1. So, this is the flipped form of the cyclohexane. So, again I start from the beginning that if you have this disubstituted cyclohexene system, by the way cyclohexene is a non-planar system, if this R2 is in the equatorial position or a pseudo equatorial position to be precise, then there is steric compression between R1 and R2. If you flip it, then R2 goes into the axial position like this. So, it is oriented upwards, and if it does that, then this interaction is gone. So, this kind of strain is called A12 strain. So, A12 strain is because this is one carbon and you can say this is 2, because they are adjacent to each other. So, that is called A12 strain, and there are many reactions which are controlled stereochemically by this A12 strain. I can show you in the model whatever I was telling you, that in the this is the cyclohexene, this is the cyclohexene, this is the double bond, this is the double bond, and then you have these 4 carbon atoms in the plane as I was saying. So, one carbon goes down, one carbon goes down, another carbon goes up. Okay, this is the system. Now, what happens? This is the pseudo equatorial substituent on my left, and this is the substituent attached to the olefinic carbon. Okay. So, you see now their diagonal angle is not 0 degree, not 60 degree also, but they have a much, they are quite in the eclipsing interaction zone, and in that zone there will be steric repulsion between this and that, and there will be bond opposition strain also. So, that makes it little unstable. So, in order to avoid this type of strain, what this molecule will do, this will undergo flipping. So, you see the flipping, what happens? The up carbon goes down and the bottom carbon goes up. Earlier this was up and this was down, now this is down, this is up. But what happens? This is the substituent which is now pointing upwards, that is it is axial. Okay. So, this axial orientation now avoids the steric compression that it was suffering when it was in the equatorial position. So, this is what is the genesis of A12 strain. Okay. So, you also know a little bit about the cyclohexene geometry now. You can actually write a cyclohexene. There are two ways of writing. One is the way I have written, another is that the way I have shown you in the model. And if you now write a perspective formula from the model, so this is what is happening. So, this is the scenario. So, this is the substituent I was talking to you, and these are the, this is the R2 and this is the hydrogen. Okay. So, when it flips, so it goes into the, this will go down. So, now the chair will the half chair will look like, sorry, half chair will look like this. Okay. So, if I number it 1, say 2, 3, correct numbering should be 1, this is 1, 2, 3, something like that. I am not following the IUPAC system, just a rough numbering 1, 2, because I want to show the allylic 1, 2 strain, this vicinal strain. So, 1, 2, 3, 4, 5, 6. So, now it will be 1, this will be 1. So, this is 2, that is no doubt 2, this is 3, that has gone down, this is 4, this is 5 and this is 6. Okay. Now, where is this R1? R2, the R2 is pointing to this side and R1 is still here. So, now this interaction is less, there is no interaction, practically no interaction between R1 and R2, but here is there is A12 strain. Okay. This is the other way to write the cyclohexene. Okay. Whichever is convenient for you, you do that. Okay. But we mostly will use this later on, we will use this type of conformer in describing certain reactions. Okay. So, that is again some kind of static stereochemistry that we talked about, that how the preferential conformation is dictated by this kind of strains. So, we have seen different kinds of strains. So, these are the additional ones. Okay. There is one more important strain that is there. Just a second, let me try to clear that. Okay. So, let us see, there is another effect like this allylic effect is there, there is this ketone effect is there. There is another effect which also tries to put the substituent in the axial position preferentially, and that is called anomeric effect. Anomeric effect. Now, anomeric effect actually the name comes from the sugar chemistry, where you know that glucose has the number 1 carbon of glucose is also called the anomeric carbon. So, let me write the glucose structure. Two forms of glucose are there. This is the alpha D glucose and there is this beta D. This is the beta, sorry, this is the beta D glucose and the other one is alpha D glucose. Alpha is when the weight is axial, other groups remain at the same orientation. So, this is the alpha D glucose. Now, in water solution, you know that this is the predominant one, it exists as a 2:1 mixture of the alpha and beta D glucose. 2:1 mixture of beta, beta is 2 and alpha is 1. So, if you take pure alpha, then this undergoes mutual rotation and ultimately it creates a mixture where this is 2 and that is 1. Or if you take beta, put it in a solution amphoteric character with amphoteric character, both acid and base character, then it undergoes mutual rotation and ultimately the equilibrium value is reached, where this is present in a 2:1 ratio. Okay. So, that is understandable, this weight is equatorial and this weight is axial. So, we know that the groups tend to assume the equatorial position preferentially. So, that is okay, but the moment this was made into OMe, say the methyl glucoside, so this is the alpha methyl glucoside, and this is the beta methyl glucoside. Now, between these, see, if you want to do this glucoside formation with methanol and take glucose, whether it is alpha or beta, because they will always be equilibrating into this via mutar-rotation into a 2:1 form. So, we expect that if I take glucose, D-glucose, and do this glycosylation, this methyl glycosylation, then I expect that this should be formed in major amount and this should be formed in minor amount, but in the on the contrary, actually this was formed in the major amount. This was found to be major. And so, what happens when it is glucose? It was wedge, as expected the wedge assumed preferentially the equatorial position, but when you convert the wedge into OMe or OCOCH3 and or OCOCH3, then what happens? The preference for the axial orientation increases. Preference for the axial orientation increases, and that is what is called, because this is happening at the anomeric carbon, and this is what is called the anomeric effect. The anomeric effect is the effect in which the axial orientation is preferred over the equatorial orientation. Okay. Now, this happens, then this happens only when you have oxygen here. If you remove the oxygen, then this was more stable than this one, but if you have the oxygen here, then this thing happens. Now, what about the other groups? Later on people found that this is a very general effect. It is, you do not need these groups. So, if you have an oxygen and then the next carbon is a stereogenic carbon and you put OMe at the axial and OMe at the equatorial, which one is more stable? It was found that the axial was more stable than the equatorial. And why is that? The explanation, there are many explanations. One explanation is the what is called the dipole, because in this case the dipole, the polarity is in this direction and the CO-OMe also in this direction. So, there will be repulsion between these dipoles. So, which is minimized in case of the axial methoxy. But there is another which is a little better approach to explain this preference for the axial orientation, and that is what is said is that, see, oxygen has two lone pairs, one is pointing towards the axial position and the other is pointing towards the equatorial. Now, if you have the OMe attached in the axial position, so you have a carbon oxygen bond. Now, oxygen orbital and carbon orbital are combining with each other. So, they can form an antibonding orbital which has a bigger lobe at the back side, and that is empty. So, now this oxygen lone pair in the axial position and this empty sigma star, they are in lateral position. So, there is a possibility that this oxygen now overlaps with this empty antibonding sigma star, the carbon oxygen sigma star orbital, thus stabilizing the system, which is not possible in case of the equatorial isomer, because the antibonding orbital will be on this side. So, there will be no interaction. So, now you have this interaction which is stabilizing the axial isomer. So, I think that is a better way of explaining the anomeric effect. So, this is another new chemistry that you have learned, this anomeric effect, that is whenever you have a system in which a heteroatom like oxygen is present in a ring, then the next adjacent carbon tries to adopt a orientation in which the electronegative group, now this is an electronegative group, that has to be important. It does not happen with alkyl group, it happens with only with electronegative group, and the electronegative group tends to occupy preferentially the axial position, and that is the anomeric effect, and this is quite important in explaining the product formation or the dynamic stereochemistry in sugar molecules. Okay. Thank you.